Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And I think for the last couple of weeks, I've been going over, the various 3D rotation and symmetry groups corresponding to the five Platonic solids. There's actually just six of these groups, three rotation groups and three symmetry groups, because it turns out that both the cube and the octahedron, those are dual polyhedrons. They have the same groups, same group structure. And similarly, the dodecahedron and the icosahedron do as well. So anyway, today I'm going to talk about the icosahedral rotation group. There's just one more of these videos I'm going to do on the Platonic solids. I'll do that one tomorrow. That's going to be on the icosahedral symmetry group. And these are the biggest of the groups that I'm going to discuss regarding the 3D groups corresponding to the Platonic solids. It turns out the icosahedral rotation group has order 60 and it's isomorphic to A5, the alternating group on 5 symbols. Anyway, let's begin. So, here, and in the book I talk about the dodecahedron. Equivalently, you could use an icosahedron. I think it's actually a little easier with an icosahedron than a dodecahedron. So what I did in my book was I showed a, kind of a 2D picture of a, like a wireframe of a dodecahedron. And, in order to show what I really want to show today is I want to, like I did yesterday, I want to show that the icosahedral rotation group is isomorphic to A5. In other words, the group of alternating permutations on 5 symbols. We could just use the numbers 1 through 5, 1, 2, 3, 4, 5. The way I do it in my book is I label the vertices of a regular dodecahedron, but there's 20 vertices. Similarly, there's 20 faces of an icosahedron, which is a dual polyhedron of a dodecahedron. So you could either talk, and the trick here is since there's 20, you only care about the numbers 1 through 5. But it turns out that we can actually use each of these numbers 4 times, and I did it here too. Let me just orient with this. So this took me about an hour to make, by the way. And I think tomorrow I'll make another one because I want to show the symmetry group, which involves a mirror image. But you'll notice that I use 4 different colors, just like I did in the book. I use 4 different colors for the numbers. So I have the numbers 1 through 5, and you notice that I have 1, 2, 3, 4, 5 going clockwise for the red numbers on 5 of the equilateral triangles making up the icosahedron. If you go to the opposite side or the opposite, vertex, you'll see that you have 5 blue faces, blue numbers, and these are going in the opposite direction. They go 1, 2, 3, 4, 5 counterclockwise. It turns out that the blue one, each blue number is opposite the corresponding red number. But then I've got also green and purple numbers on the side, and the green and purple aren't as nice. They don't form groups of 5 all connected like the red and blue ones do. But it still has a property that we're using all 20 faces. We're using each number 1 through 5 exactly 4 times, and the way I colored them on my icosahedron, the same way I did on my book for my dodecahedron. There's what do I want to say? There's 1 number of each color: red, green, blue, and purple. I think in my book I use red, orange, green, and blue. But, it doesn't really matter. I'm using 4 different colors. So I think it's probably going to be easier for me to demonstrate with the icosahedron. What I do in the book is I go over all the possible rotations of the icosahedron. Might as well tell you what the types of rotations you can get. So remember, you always get the identity. That's the transformation where you leave it alone, don't do anything. But then you get these 20 fivefold rotations. So for instance, for these 5 red numbers, I could rotate the icosahedron 72 degrees. That's 1/5 of a complete circle, either clockwise or counterclockwise. But I could do it 72 degrees, 144 degrees, or clockwise, or I could keep going. 216 and 288. That's equivalent to 144 degrees and 72 degrees counterclockwise. So I could think you can see that for every pair of opposite vertices of this icosahedron, there's exactly four fivefold rotations. But then remember, there's 12 vertices of a regular icosahedron, just like there's 12 faces of a dodecahedron. That means there's 6 of these axes, because each axis goes through a pair of opposite vertices. So we really have 4 times 6. Is that right? Yeah. 4. Is this right? I hope I'm not getting it. But it looks like I just have 20 here. I'm not sure why I just have 20. Was it 5? Sounds like it's wrong. I don't know what's wrong. Yeah, there's 12. I know there's 12 vertices of a dodecahedron, so I don't know why I'm only getting 20. There should be 24, I think. Unless I made a mistake in my book. I gotta double check all this. So maybe before, while I'm thinking about this, so these are the fivefold rotations, but then you've also got threefold rotations. So for instance, you could rotate about a face. Let's just look at the one face, the red one. You can rotate 120 degrees or 240 degrees, still make it look the same. And we've got 20 faces. So that's going to give you 40, is that right? It looks like I only showed 20 here. So I'm confused right now. Sorry about this. Having a little brain fart. Okay, we have okay, now I know what I did wrong here. There's 20 faces of an icosahedron, but the axes were rotating about pairs of opposite faces, and there's only 10 of those. There's 10 axes passing through pairs of opposite faces, centers of pairs of opposite faces. And remember, I just said that there were 2 possible non-trivial threefold rotations for each of those 10 axes. That gives you a total of 20. So there are 20 here. That I did right. And then the other type of rotations you can get are the rotations, the flips about an edge. And there's 30 edges of an icosahedron. That means there's 15 pairs of opposite edges, and for each of those you get exactly 1 non-trivial rotation. So yeah, maybe in my book I left out 5. I didn't think I made any mistakes in my book, but it looks like I did. Unless maybe I didn't list them all on the bottom. Maybe that's probably what I did. Yeah, I think I didn't list them all. I mentioned 4 and then I listed another 20. So now I understand what I did wrong. Sorry about this. So there are 24. Like I said earlier, there are 24 non-trivial fivefold rotations. And there's 20 non-trivial threefold rotations, and there's 15 non-trivial pairs of transpositions, which correspond to edge flips. Why are they pairs of transpositions? Maybe I should just go over that. And I didn't even really go over why the threefold rotations just give you rise to a single three cycle. I mean, I think you'll just have to take my word for this. When you do a 3 cycle, or when you do any of these transformations, it turns out that remember there were 4 of each number. It turns out that it doesn't matter if you're looking at numbers of the same color, which I do in my book. They all transform in the same way. It's kind of a miraculous thing that they do this, but they do. I don't think it works for the way I colored the faces of the icosahedron, though, because I didn't color them the same way as I colored the vertices of the dodecahedron in the book. I guess I could have tried to do that today, but like I said, it took me an hour just to make this. I guess I could have been a little more meticulous and made sure I did the coloring right the same way I did in the book. But you'll just have to take my word that for each color of numbers, you get the same cycles, you get the same transformations. So these are the 24 5 cycles you get corresponding to non-trivial 5-fold rotations, and then these are the 20 3-fold rotations. These are the numbers that get changed. Um, yeah, I think you'll notice that when you do a 3-fold rotation, for instance, if you did a 3-fold rotation like I did before about the red 1, there's a red 1 and there's a blue 4 opposite. Uh, those are fixed. So the 1 and 4 are fixed. So if I did this 120-degree rotation, the only numbers that are getting permuted are 2, 3, and 5. So you'll either get 2, 3, 5 or 2, 5, 3. And similarly for every other pair of opposite faces. So that's why these give rise to threefold 3 cycles. And then for the edge flips, why do you get a pair of transpositions? Well, let's just try to do one. Here's 4, 5. On the other side is 2, 1. If I do this flip, 1, 2, 1 and 2 get transposed, and 4 and 5 get transposed, but 3 gets sent to itself. I don't know if you can see that, but 3 is fixed by this. So I think you'll just have to take my word for that too. Every edge flip, I think I maybe discussed it a little better in the book, but every edge flip gives rise to a pair of transpositions. And notice that these are all even permutations, and this should be all of them, by the way. So let's just add them up to make sure that we get the right number. So we have the identity, which is one element, and then we have 24 5-fold rotations. That's 1 plus 24, 25. And then we have 20 3-fold rotations. That's going to make 45. And then we have 15 pairs of transpositions. That makes 60. So yeah, we do get all 60. We get all 60 even permutations of 5 symbols. So this is, I think I just proved that the rotation group of a regular icosahedron, or equivalently a regular dodecahedron, is isomorphic to A5. That's what I just proved. And I think you could convince yourself of that. Just maybe you should try to make one of these. They're not that easy, but I invite you to try. It's kind of fun to make these platonic solids, I think. Yeah. So now I'm just going to have one more lesson on this tomorrow. I'll talk about the full icosahedral symmetry group, which turns out to be isomorphic to S5, the full symmetric group on 5 symbols, which has order 120. That's a pretty big group, and I think that's the biggest finite group I'm going to mention in this chapter. So anyway, we're done. Thank you for watching. Long live math, and I'll see you guys next time. Bye.